Okay, perfect. So, hello everyone. My name is Oleh Yermakov, and indeed, I will tell more about the general, maybe mathematical tools in photonics, but more about my own specific research, which are mainly more physical than mathematical. But anyway, some simple ideas I will cover, I hope. So I will tell three stories. The first story is called optical beam shifts. So it's well known, yes, that in physics we use the model of plane waves. It assumes that we have infinitely flat wavefront of the propagating electromagnetic wave, and electric and magnetic fields are oscillating in orthogonal directions, or orthogonal planes. And we can use Snell's law and Fresnel equations in order to describe all things which happen with such a plane wave incident at planar interface. However, in real life, we don't have the plane waves. We have only the optical beams, which are the set of plane waves with different propagating wave vectors, with different plane of incidence, with different polarizations. And this conventional physics of Snell's law and Fresnel equations do not work in this case. It could not be applied in this case. And for instance, there are some phenomena which could not be described following the standard Fresnel equations. For instance, it is the shifts of optical beams. It could be longitudinal shifts or transverse shifts. So there are two types of shifts. The first is Gus-Hankin shift. It is proportional to the Fresnel coefficient phase. Yeah, it is the longitudinal shift. And the second one is transverse shift, so out of plane of incidence. It was theoretically predicted in 1955 by Belarusian physicist Fedorov, and then experimentally discovered by Imbert. And it is proportional to the gradient of Berry phase, and the very popular phenomenon today, which is widely studied, so-called spin Hall effect of light, or photonic spin Hall effect. It's just the partial case of the Imbert-Fedorov shift. So you can see that 2 points. First, these shifts have been discovered quite a lot of time ago, so 10 years, thousands of scientists published thousands of articles describing this phenomena and constructed, of course, analytical models. And secondly, Gus-Hankin and Imbert-Fedorov shifts have different natures. So first is proportional to Fresnel phase, second to the Berry phase. So these are separate phenomena. However, there are several recent experiments which have shown anomaliously large shifts at near normal incidence, when the angle of incidence is just several tenths of degree, or at least less than 1 degree. And the existing theory does not explain this. So it encourages us to develop the theory and construct the extended theory, which takes into account this partial case. So we've followed so-called Jones matrix formalisms. So first, this Jones matrix is a composition of 3 matrices. So first, we go to the system coordinate of the central plane, central constituent plane wave of this beam. Yeah, we calculate the Fresnel coefficients for the particular wave, take into account the deflection of no central wave from the central one, and then we go back to the initial laboratory system of coordinates. So in such a way, we can calculate the scattered electromagnetic field, and the shifts are calculated as the just deflections of central mass of the beam according to the quantum mechanical definitions. Here, this line corresponds to the linear shifts, displacements, and the bottom line to the angular shifts, so deflections. And in standard theory, this angle phi, which is a deflection angle of no central wave from the plane of incidence of the central wave is defined as follows. However, to be strict, the correct formula is the following. And indeed, here the theta is the angle of incidence, mu and nu are the out of plane and in plane deflections of the particular wave. And usually, for this case, for instance, they are much smaller than the angle of incidence. So if we put theta much bigger than mu, we will come to this formula, yeah. But of course, for some cases, it's exactly when the angular divergence of the beam becomes comparable with the angle of incidence, we should follow this formula. And another story that very phase in this case is defined exactly following this formula. So both shifts will follow the same nature. We can see it here, for instance, the final formulas for the shifts as the following. Yeah, this is Stokes parameter, so this is polarization. Tau, this is some material parameters, and some angular dependence described by these functions, which are pretty the same. This is the final dependencies for the shifts, which well described all recently observed phenomena, which are not covered by the standard theory. And the main features here are first, that Gush-Hankin and inverse Fedorov shifts in this case have the same nature, the same origin, which is the singularity of Berry phase. This exactly comes when this denominator goes to 0. And the second story is that we show that Gush-Hankin shifts is possible at very small angles, because according to the standard theory, it happens only after the critical angle of total internal reflection. So this is a quite large angles. Here we see it at the small angles. And here are also some very interesting polarization structure of this shift, but I will maybe skip it. So currently this work is available in the archive and under revision in physical review letters. The second story is devoted to the fibers. So it's well known, yes, that refractive index is defined as the ratio of speed of light to the speed in the special medium, yeah. And for different medias, the refractive index is different, but in visible range, it usually does not extend 4. Yeah, and if we will illuminate from more dense medium, so from the medium with higher values of refractive index to the less dense medium, yeah, we can observe under some angles, after some angles, the total internal reflection phenomenon when all light remains in the first medium and doesn't transmit to the second medium. And this principle could be easily observed just with laser and water, for instance. And it is the basis of optical fibers, where we use 2 types of glasses, so-called core and cladium, with slightly different refractive indices in order to hold the propagating light and transfer the light at large distances for tens of kilometers. So optical fibers are widely used in telecommunications. It is the main tool of our information transferring, yeah, because the data transferred by antennas, GPS, or radio is much smaller, of course. But also fibers are used in detectors in different areas, particularly in the medicine, in endoscopy and laparoscopy, yeah, to analyze some in vivo or especially closed systems. However, there is a problem, which we defined as small encoupling efficiency. So what do we mean? Let me imagine that I fall with plane wave or Gaussian beam to the end face of fiber. Yeah, what is the encoupling efficiency? So the efficiency of the transformation from plane waves to the guided fiber mode. Indeed, under normal incidences, it's almost ideal, but it rapidly drops when the incidence angle increases. And for the angles 15-20 degrees is too small to be used for practical application. And of course, it significantly limits the practical applications in sense, in spectroscopy, and some medicine applications like endoscopy, because it is impossible to collect the light into fiber under large angle of incidence, more than 15 degrees, let me say. And so our main result is shown just at this figure. So we structured the fiber and achieved the enhancement of light coupling efficiency by several orders of magnitude. Here are the experimental results. But let's go step by step now. So of course, there were several attempts to increase this coupling efficiency by structuring the fiber and phase. And here it is one of the most successful, where the authors put the periodic array of plasmonic metallic nanodiscs. And here are the experimental results of the research. So orange dots corresponds to the unstructured fiber, and blue dots to the fiber empowered by this plasmonic periodic array of nanoparticles. And you can see indeed that the coupling efficiency is greatly enhanced in this case for different angles, but at the same time, the coupling efficiency is still very low, especially at the large angle of incidence. So it's 10 to minus 4, 10 to minus 5, and large angle 10 to minus 6. So we aimed to achieve the great coupling efficiency at large angle of incidence, where this is the most challenging issue. And we structured the fiber and phase it by such actual symmetric photoelectric nanostructure, which acts as a diffraction grating, which first diffraction order coincides with the axis of the fiber, and defines the effective coupling area as the ratio of power of the guided mode measured inside the fiber to the intensity of the incident light, and the plane wave coupling efficiency as the ratio of this effective coupling area to the area of the mode, which is well known by the passport of the fiber, but in practical it's slightly larger than the area of the core. And we introduced some very simple analytical model to represent that it works. So we calculate the overlap integral between the tangential components of electromagnetic fields of the guided mode itself, guided mode of the fiber, and the field scattered by this nanostructure. So we calculate the surface integral at the interface between the nanostructure and fiber. So at the fiber and facet, and so for guided mode, it's well-known analytical solutions which could be well approximated also by Gaussian functions. But for the scattered field, we follow the simple formalism. So as well as all the electric structures like such as silicon, nitrate silicon, or polymers have negligible absorption losses in the visible range. So we just first calculate the transmission coefficient for the light in the absence of the structure, and then multiply it by some phase factor, where this phi function is just a step-like function, and this peaks, the steps, responds to the rings arrangement. So in simplest words, it works like this. And after that, we apply the proper normalization. And this very simple model allowed us to optimize the design, to change the width, height, and period of each ring of the ring array, and to define the most optimized design. Then we will also check it by the numerical simulation and apply some advanced optimizations. And finally find the base design, which was done by using the combination of electron beam lithography an ion beam etching. And here you can see the same image of the fibers nanostructured by these ring-like structures with different number of rings. Here's 5, 7, and 24 rings. And here is the main result, where you can see the dependence of plane wave coupling efficiency on the incident angles for different polarizations, T and TM. Here is experimentally measured results and numerically calculated. This gray dashed line corresponds to the bar fiber without nanostructure, and color lines to the fiber with different number of rings. And it's first, it's easily to see the great enhancement of the coupling efficiency at large angles of incidence up to the percent level. Secondly, we can see that it's almost independent from the polarization of the light, which is also obvious due to the actual symmetry of the problem. Okay, I will maybe skip this. These modulations could be also easily explained. And we also calculate so-called integral large angle coupling efficiency, which is defined as follows. So we just calculate the coupling efficiency in the finite range of incident angles, starting from the gradient incidence. And it just states that for the case of structured fiber, we just have to use the range of 10, 15 degrees in order to achieve the maximum coupling efficiency. This is important for practical applications. And now we would like to do the same story with some more advanced optimization, but to achieve the local coupling enhancement, not at the some angle, but at any angle, so in the whole angular range. To do it, we use some aperiodic structure, which gives us multi-channel diffraction, many diffraction orders. So, and it works at any angle of incidence, but I will know this very new results, so I will not show them in detail. So these results combine the fiber optics in nanophotonics and has been highlighted by the ACS Photonics journal, where we got on the front cover of the October issue, and got to the so-called Optics and Photonics News Journal December issue, which selects 30 best, the most exciting optics researchers during the last year. So it will be published in December. And the last part is devoted to my major area of research, to the study of surface waves at two-dimensional systems and structures. So why we need to do it? Because classical optical devices such as lenses, mirrors, filters, polarizers become too thick, functional, and fundamentally limited. It emphasizes the emergence of resonance photonics, which uses some wavelengths, so much less than wavelengths thickness, multifunctional structures which can overcome some fundamental limits, such as, for instance, diffraction limit by using evanescent fields. And resonant photonics platform consists of metasurfaces, metalenses, different nanostructures, nanoparticles, and my research focuses especially on metasurfaces, which are two-dimensional periodic arrays of deeply subwavelength scatterers, enabling to manipulate light on demand. And of course, the study of metasurfaces could be divided into two branches in the far field. Yeah, in this sense, metasurfaces are studied as the transformers of the plane waves. So these are reflectors, refractors, antennas, lenses, etc. If we look at the dispersion diagram, yeah, the dependence of energy on the momentum, we will work in this zone inside the light cone. However, for some tasks such as integrated circuit, tensions, and chip devices, and any other planar technologies, one needs to control light over a surface almost in two-dimensional space. And in this case, we should go under the light cone to the so-called near-field spectrum, yeah, which gives us the localization. And one of the best carrier of this localized light is surface plasma polariton, which is a hybrid state of light and matter, and it could be understood as just surface electromagnetic wave, which is the direct analog of the water waves excited after the stone is dropping into the water. Okay, so there are different applications for surface waves, sensing, sorting, quantum physics, optomechanics. Sorry, say something.
1 minute more.
1 minute. Okay, okay. So then 1 minute. Okay. Maybe I will stop here because here I just in the beginning of the short story. So sorry for this. Yeah, I will better answer the questions.
Yeah, time for the question. So maybe again, I will ask. Several years ago, I was having discussion about abnormal phenomena during high energy transmission in glass fibers, especially at the contacts. Is this solved already, this problem? Transmission of high energy light, high intensity light.
Yeah, indeed, there are many. So if you talk about the problem of coupling efficiency, yeah, fibers, there are many ways how to increase this coupling efficiency. For instance, very easy one is to use just oblique cutting. I don't know, can I draw with something like this? Yeah. But the question is, in this case, it will work only for the incidence from this side, right? And practically, you need to use plane end phase because you don't know from which side light goes. Yeah. For instance, it is important for single photon collection, for endoscopy, some random distributions of, I don't know, luminescent particles which you have to analyze. So for such applications as sensing, endoscopy, etc. In this case, you should be able to collect light of arbitrary polarization going from arbitrary azimuthal angle, so from this direction, from these directions, and from arbitrary angle of incidence, yeah, something like this. And this problem was not solved.
Thank you very much. I don't see more questions. Thank you very much.